This is Mr. Mitchell with a video about Isaac Newton's three laws of motion. Now, these laws of motion are the relationship between motion and force. Now, a force, every motion is related to some kind of force. There's not just random motion without some kind of force. And Newton spent a lot of study on the relationship between motion and the forces that are behind the motion. The very first of these three laws, let me take care of this erasing right here. The first of these three laws is this one. A body at rest tends to stay at rest. A body at motion tends to stay at motion. That's the first law of motion. Here we have the soccer ball. The tendency is if it's at rest, not moving, then it will tend to stay there until a force is brought upon it. Somebody's foot kicking it, some kind of animal nudging it, some kind of whatever force would make it go. And here we have a soccer ball that is moving. This body tends to stay in motion. And it would stay in motion in a straight line until another force acts upon it. Now we know soccer balls thrown in the air don't go in a straight line, but it is gravity which pulls them down. So gravity, of course, is going to be a force, but if you didn't have the gravity, it would tend to go in a straight line until a force acts upon it. So if you think of the planets tend to go in a straight line out in space if it weren't for the gravity which keeps them circling around the sun. So at any given point, if the sun were not there, the Earth and all the other planets in their motion would tend to just go out into a straight line from wherever they happen to be in the rotation at the time. Now this is often called the law of inertia, and we'll get to inertia here in just a little bit. But here's another commonly used example for Newton's first law of motion. You see here we have this coin. Well, I hit the wrong thing. Here we have this coin on top of the cup, which has a little note card, I suppose you would say, in between it that's keeping it from falling. So that coin is in rest. It is not in motion, it is in rest. So according to the first law, it tends to stay in rest. And a lot of people point out that whenever you have the person flick the card out from under it, the coin still tends to stay at rest. In other words, not go flying out with the note card that happened to be up from under it. And I don't know why I have two pages right here doing the same thing. Here's another one. Okay, let's talk about inertia and friction. Here's an interesting analogy for inertia. Inertia is the quality that makes bodies want to do the same thing. In other words, whether inertia makes something at rest want to stay at rest, and makes something in motion want to stay in motion. The reason they have this as an example of inertia, we have this person who presumably was on the motorcycle going fast. It hits the tires, but the body tends to want to keep going in motion. And if it weren't for Newton's first law, for inertia here, that quality which makes up that first law, this person would be stopping with the bicycle. But since you have no force in which to stop it, besides gravity, which will eventually pull him down, then you have this body that wants to remain in the same motion in a straight line. Now, friction is, well, a little bit opposite, but not quite. See, if you have this box here and you want to move the box, friction is what drags it down. Sometimes you hear of the word drag meaning the same thing as friction. It's the force that acts opposite to movement. It kind of drags it down. Now, sometimes that's inertia and sometimes it's not, because the first law states that if you have something that's in rest, it will want to stay in rest, and that is inertia. But if you have something moving, it wants to stay in movement. That's also inertia. So kind of sometimes inertia and friction are similar, and sometimes they are not. Okay, let's take a look at Newton's second law of motion. Second law of motion says, it talks about force. Force equals mass times acceleration. So mass, how big, how large something is, and acceleration, how fast it is moving. So you could have a large body with a lot of acceleration, a large body with a little acceleration, or vice versa. You could have a little body with a lot of acceleration, a little body with almost no acceleration. So you can see down here we have some calculations. And let me go over here and show you what the quantities of unit are. Mass is commonly used in kilograms. Now we often go mass in weight, but we're going to use kilograms because of the scientific aspect of it. And acceleration, we have mentioned, is meters per second squared. See, the force is measured in newtons. Before we get to the calculations, I want to talk a little bit about this. Consider pushing an empty shopping cart as opposed to pushing a full shopping cart. The full shopping cart is harder to get started, but once you get going, it has more force behind it than an empty shopping cart. A full shopping cart at a large force will dent in a car worse than an empty shopping cart would because of the mass. So we end up also using pounds as a unit of force on occasion. And I'll just go ahead and put that 1 pound is 4.448 newtons. So if we say 1 pound of pressure is equal to 4.448 newtons. I don't think it comes into play in this particular exercise here, but I know it does at a different time. Okay, so if force equals mass times acceleration, we have F equals ma. Your bicycle has a mass of 9.1 kilograms. You accelerate at a rate of 1.7 meters per second squared. Calculate the net force that is accelerating the bicycle. Sounds like a pretty straightforward one. Force equals mass in kilograms is 9.1 times, looks like 1.79 meters per second squared. So kilograms times meters per second squared is exactly what we're looking for right here. So I'm going to go down here to the dashboard. That is, let's see what that was, 9.1 times 1.79. 9.1 times 1.79 equals. So it looks like 16.289 newtons would be the answer. 16.289 newtons. Okay, so that's how we do that. Now we have a number 2 and we have a number 3. Number 2 is meter per second square and 800,000 kilograms. So on your own, we do not have any questions with this particular video, but on your own, I'm going to have you turn in number 2 here. You need to calculate the force. It's just multiplying it out. Now number 3 is a little bit different. I'm going to have you do that one also. So 2 and 3 you show me for your homework. A runner has a mass of 89 kilograms and produces a force. So we know the force. We know the mass, but we do not know the acceleration. Now you saw in an earlier video how you calculate that, how you find this acceleration right here, where you divide both sides by m. So I'm going to have you do that one on your own also and see how well you do. let's go to something called free fall. When the only force acting upon an object is gravity, the object is in free fall. Near the Earth's surface, gravity is 9.8 meters per second squared. Now that doesn't mean that if somebody drops a ball down through here, it will travel 9.8 meters every second. The fact that it's squared means for the first second it'll fall 9.8 meters. Then for the next second it will expound upon that and make it 9.8 times 2 meters. Then for the third second you add another 9.8 meters and so on. But here on Earth it's 9.8 meters per second square, and that's because of the gravity of the Earth. Now we have already calculated force equals mass times acceleration. You can find the force of weight using what looks to be almost the same example here. The acceleration, if you are in free fall, is going to be called g, gravity. So anytime you use W equals mg, the g is going to be that 9.8 meters squared. So if you were looking to find the weight of something, you multiply it times the mass times the force of gravity. Now, many times people confuse weight and mass. Weight and mass, well, they're almost the same. But the mass of an object here on Earth is different from the mass of an object on a different planet. And even here on Earth, you have different places which have different rates besides 9.8. Here on the Earth's surface, the value of g is going to be 9.8. But if you get, say, 5,000 kilometers above the surface, the value is only going to be 3.8. So the farther away from the center of the Earth you are, actually the less you weigh. Let's take a look at something else right here. And here's what it is on different planets. On Earth, you know, we have 9.88 meters per second squared. So on Mercury, it would be only 3.61 meters per second squared. So what would you weigh on Mercury? Well, let's see. If you take a person who weighs 150 pounds and figured out how much they weigh on Mercury, first of all, the pounds will have to convert to kilograms. So to make a long story short, to convert to kilograms, you have 150 divided by 2.2. So that makes 68.18. So 68.18 is the mass. And the gravitational pull here would be 9.8, but on Mercury it would be 3.61. So you're multiplying 68.18, almost put the wrong figure here, times 3.61, and let's see what that turns out to be. Okay, times 3.61 equals, so that'd be 246 newtons. 246 newtons. And remember, a newton equals 1 pound equals 4.448 newtons. So we'll divide out 246 divided by 4.448 equals 55 pounds. So instead of 150 pounds like you have here on Earth, you would only weigh 55 pounds on Mercury. And that's how that would go. Oh, let's see if there's anything else we have here. Yes, I believe we have the third law of motion. The third law of motion is for every action, there is an equal and opposite reaction. Here we have a balloon. We have the action which is running out, and the reaction which is making the balloon go up. You know, if you release that balloon, it's going up in a different direction. Here we have two people on ice skates. Our roller skates would do the same thing. What happens if they push together? Neither of them stay in the same spot. One is going to go that way, one is going to go that way. The same thing for like a rocket.